All right. So very good afternoon, students. So we're going to continue with our evaluation criteria, which is on the error loss function and also the cause function. Is actually used as part of the machine learning evaluation. So of course, when you actually develop your model, you train your model, and you want to evaluate the performance of your model. So that you need a way to measure how well it actually predicts the observed data, right? So therefore, we need to actually quantify. How do we actually quantify the predicted response? So for the supervised, currently we are looking at the supervised learning, whereby we have the label data, right? Do you remember what's the label data? So label data is the data attributes that you want to predict. So how good is your prediction? How good is your model's prediction? So in order for us to evaluate that, there is a cost function that is actually used, known as the mean squared error, MSE. So squared error means you're just finding what is the squared error, the difference between the actual value and also the predicted value. So that's a squared error. So if you look at the mean squared error means you are looking at all the average of all the squared error. So later there's one diagram that actually shows you how to actually calculate this. Now this, how do you calculate the mean square error, and also the equation is very, very important. So when I say very, very important, so make sure you take note of it. So you need to know the formula, you need to know what actually it means. So in later point of time, I'll actually prepare another notes for all the evaluation criteria, an explanation behind the evaluation criteria on what should be the expected value. Should it be a smaller value, or should it be larger value, or things like that. But as of now, the mean squared error formula and function is very, very important. So make sure you know about it. Whereby what n stands for? N is actually the total number of observation, the total number of rows that actually have. Of course, fx and also the y. You can see here that is fx and also the y. So the fx is actually from the model, the actual value that you get from the model, minus the actual value. What is predicted minus the actual value, you get the difference, right? And you try to find the squared. So where have you seen this formula before? What formula is this actually? Pythagoras. Of course, Pythagoras is a slightly different format. This is actually for distance, right? You're just finding the distance between one coordinate and another coordinate. You minus and then you take the square to find what is the distance. So what is this doing? 1 over n. N is all the total number of observation that you have. If without this, then you're only looking at the squared error of 1 point. What is a squared error of 1 point? How much does it deviate from the actual point? But if you're taking the mean squared error, you're looking at all the points and try to sum it all up. So you can see it's a summation of all the square root errors of all the points. So of course here some terms are there. There is one diagram, so that will actually show you what these are. So the loss function and cost functions, these are actually both are based on the difference or error between the model and actual labels. So meaning to say you're trying to find what is the difference, right? But these terms, loss function or cost function, they can actually be used interchangeably. They actually more or less means the same thing. Whereby loss function is defined for one data point, and a cost function is the average of all loss function. So in this way, the mean square error is which one, do you think? Is it a loss function or is it a cost function? It's a cost function because we are taking the mean averages of all the square root errors, right? So therefore, the mean square error is actually a cost function, and you have this term, the predicted value minus the actual value by the power of 2. This particular term by itself Just that term, this one. This is a loss function. Why is it a loss function? Why is only this one known as a loss function? Yes, it's only taking one data point, right? But if you look at the earlier one, the cost function is when you sum it all up and take the averages of all. So this becomes the cost function because it's taking the overall. Is that okay? So here's the diagram that actually show you what it actually means. So these color dotted points, these are all the actual data. And the straight line here is from your linear model, the line that actually represents. So linear model means what? You'll get a straight line, that's a linear model, right? That's a straight line you actually get. But what is it actually trying to do? The linear model is a straight line. Sorry for those in the recording one, I can't capture this. This is actually one. This is the linear model, right? Straight line. So what is it trying to do? It is trying to get the model, position the model in such a way that all this difference, the squared error, for one is loss function. This is for one, right? If you take for multiple points, then it is the mean squared error. So what is it doing? It is trying to come up with a model that all these errors are minimized. If the same straight line, if it's like this, it's just from here to here. Now it could minimize here and here, but it maximizes these 2 points. So in other words, you try to find what is the balance, an equation that will best represent this linear distribution. Of course, now there's only like 4 points. So Steve, you try to fit in the best stuff. You managed to get the point? So how it actually forms this line in this particular way is by minimizing. So whatever model that you get, that model is actually based on these data points. Based on these data points, when you do a linear regression, you will train the model. When you're training time, you will see that it will actually shift. When you're training, it will shift. You'll try to find what is the smallest value. And that become your model. Is that okay? So whatever I mentioned is what is trained here. So the model is actually trained in such a way that the cost function is minimized. So that is actually the point. So once you actually, assume a particular model, in this case, of course, we are looking at the linear regression. The next important thing is, how do you actually assume a model? Basically, whether you look at your labels right. Remember the supervised learning and unsupervised learning? If you're looking at supervised learning, which means you want to predict something, right? And if you're looking like, for example, the label. What is a label? Label means is the attribute that you want to predict. In our previous class, we saw that the house price is something that we want to predict. So because it's a continuous data type, so we are looking at linear regression. Of course, once you have identified the type of model that you actually want to use, one of the important thing is to find what parameters that we want to actually use. Of course, some of the assumption that we actually will assume is most of the data set approximately you may have a linear relationship with the target variable. So if it has a linear relationship, how do we actually know this? How can we know whether the data set has a linear relationship with the target variables or not? Do you remember the earlier scatter matrix plot that we actually did? We were able to see with respect to each attribute with respect to the price. We saw that the distributions are linear, right? But not all. Not all attributes are having a linear relationship, right? So if you're having a linear relationship with a target variable, then we can assume that the model that to be learned is a linear model. That's one way of visualize. Through visualization, we can actually see what kind of relationship that the other attributes have with respect to the target variables. Now, this is the same example that I've given before. If we only have one input variable, then the linear model can be mathematically described as an equation of line. There's only one, right? Whereby the parameter m is the slope, c is the intercept, and x is the one input variable for you to get what is the y. Right? This is very simple. So these two parameters, which is m and also the c, the linear model, for these two parameters of the linear model have to be learned to find the optimal line that passes through the data points in such a way that the error between the line and data points are minimum. Like the earlier graph I've shown you, right? That's why when I say when it's training time, the slope will change and the intercept will change. But it'll try to find the right slope and the right intercept in such a way that all the square root errors, the mean, the average of all to be minimized. And that would be the best model to represent. So even if you have multiple inputs, that means you have multiple inputs, not only just one input, and if all of them have a linear relationship with the target variable, then still you can construct a linear model like this. You have multiple slopes and multiple x. So in this way, then now it becomes a task that is actually fit for machine learning, where you have a lot of variables that need to be optimized, right? So in that case, it becomes a multivariate parameter learning problems. So this is much more computing extensive. It actually uses much more combinations. But deep learning is actually able to do that. Machine learning able to do that, not deep learning, sorry. Of course, deep learning can do that because it's based on neural network. So we are looking at the feature selection and extraction. So still in the same topic of, okay, identify the label that you want to predict. Now, which attributes that we want to actually extract. So the process of feature selection, why is it important? Because you can remove unnecessary features from the data set. So any example of unnecessary features from the data set? For example, like the housing one that actually we saw. Let's see, do we have that or not? If you look at this data set, what are the things that you think won't be useful? Sorry? Too smaller. Which one do you think that won't be useful? Address. Yes, very good. Address. Why do you need that? You can't actually take into address as a price limit, as a attributes that actually relate to the price, right? So like this, whenever you look at the data set, you need to look at student ID, for example. It doesn't have any meaningful impact. Student ID are all unique. Address are all unique. It's not going to have any type of relationship. So, and also we have actually seen previously method based on correlation between features to select relevant features, right? We actually did the univariate, bivariate, and also multivariate. And we have seen how the distributions is all like. So you can actually see whether does it have a linear relationship or it doesn't have a linear relationship. Of course, some machine learning methods can be used for the feature selection. We will see that later. So in order for you to get a successful or accurate machine learning algorithm, of course, the point number one is to make sure you select the correct model. And you need to have a good data to train the model. If your data is bad, if garbage in, garbage out, that's what you're going to get. And the process to obtain good feature is known as feature engineering. So which actually involves what? Selecting the correct features and extracting and performing some transformation on the select extracted features. So that is very important. So in terms of definition, if you look at the feature selection means what? It means like you want to select the most relevant and also useful features. And we have done this using visualization as well. And there is also another one which is known as the feature extraction and transformation. Now this one is combining some existing features to produce better features. For example, I think one of you earlier in the project one chose one of the target variable as the wine quality outcome, right? But the wine quality is actually in terms of numeric value. So you need to do some transformation to it to make it into categorical. Bad, average, good, exceptional. So you need to do some transformation to that so that you can actually try to categorize. In some case, there is also dimensionality reduction algorithm. We will see this later on. So when you have, so dimensionality reduction actually is referred to the columns, not rows. So when you have a lot of attributes, so that increases your computational power. Not, of course, the row also has effect, but the more columns that you actually have, it means what? You have more x, x1, x2, x3, x4. So the more things that the machine learning have to handle. But there is also a way on how you can actually reduce the dimensionality, and we'll look at what are the benefits of dimensionality reduction, especially when you're having a huge data set. Now we are also looking at this underfitting and overfitting. Remember in the previous class we did touch on this underfitting and overfitting. So this underfitting and overfitting, they are one of the most crucial factor that causes a machine learning algorithm to actually perform very poorly. So what is the main objective of good machine learning model? Is to generalize from the training data to the unseen test data to make prediction. So remember we looked at this term generalize. You want to get a model that is generalized. That means not biased towards a certain set of data from the training data set. So when we look at the term generalization, it means the ability of the model to actually perform very well on the test data. So if the model is too simple to capture the real trend of the data, then what we say, it is underfit. That means it's not really representative. So the model is unable to, it's only able to predict the one from the training data, but from the test data, it's unable to predict well. So that means your model is underfit. On the other hand, if the model is very complex and it captures every single data points, especially here for example, looking at linear regression, if you have like outliers and if your model is capturing all those outliers, then what we call as this model is actually overfit. Too perfect. Any point you put, you get 99.9, 100% prediction, 100%. So when you get like that, you shouldn't be too excited. You shouldn't be thinking that, oh, my model is so good. It could also mean that your model is actually overfit. Maybe you train 99% of your data to the training and you just let one as your testing data. Of course, your model will overfit, right? So you need to find the balance. So this is a visualization to show this is an underfit. The data distribution is like this. If you draw a line like this, it is not really representing the actual data distribution. So if you test the data using this region data, of course you'll get good. But if you test data from around this region, it will perform very poorly because your model is around this line. Now B is an optimal model which represents the distribution of the data. So in this way, whenever you take any data points, it will be able to predict very nicely. Now this one, A, underfit, from what we learned earlier about the MSE, mean square error. What do you think the mean square error of this algorithm model will be? High or low? Remember what is mean square error? Is actually taking all the difference between the actual point predicted and finding the average, right? So this one, the model is here. So here you'll get very high. Remember, you're taking the square of the difference. So which means it will have a very heavy penalization on the high error. Whenever there's a high difference, you square it. If you square it, you'll get a large number. So that's a penalization for getting that. But you see this one, the curve very nicely comes like this, right? So this model is an optimal model. It represents very well. So whenever you get all this MSE for all these points, you'll get, okay, more or less the same. But look at the C. This is an overfit. This line, whatever value you put, you'll get almost 100%. You get very, very small MSE value. So this is a visualization. So therefore, we don't want to get an underfit and we don't want an overfit. So we need to get an optimal model, right? We're done. Okay. So let us go into, why is it not connected? The first part, which is supervised learning and the regression. So we look at supervised learning first, and then later we will look at unsupervised learning, right? So the first thing under supervised learning, there are many actually, but we are looking at the main two types, just classification and also regression. Now, if the output label or the label that we want to predict, if we have the continuous range, what we want to do? Classification or regression? So continuous, this is very important for you to identify. So make sure this aspect is important, because there will be question in final giving you a certain set of problem and then ask you what type of model that is suited for it. So you need to justify why. So that's why I'm asking questions. So if you are looking at supervised learning, you want to predict something, and the output label, if you have a continuous range of values, then it is regression. So otherwise, if it's not regression, if it's categorical, then you'd use classification, right? So if the relationship between the input features and also the output target variable is assumed to be linear, then of course the regression, the line would be linear. So even under regression, there are two. There is linear and also non-linear regression. So we will see on that's known as a logical regression, linear regression and also logical regression. We will see that also later on. So now we will actually look at the linear regression. It's quite a famously used regression method. So to actually implement the linear regression, we need to import the libraries and packages. I didn't send you the. Yeah, so thought I forgot something. This one. So the first thing that we want to do is, of course, we are going to import numpy, the numerical pi, uses np. Then we're going to import. We're going to do some plotting also. Matplotlib .py plot, and we use as a function as, sorry, this is matplotlib. Let me me enlarge this. Able to see, but oh. So matplotlib .pyplot splt. Now this one we are going to use for machine learning. We are going to import a library known as sklearn. We're going to scikit-learn. The scikit, so scikit-learn. So we import that as sk. So all these machine learning algorithms functions are all comes under this scikit-learn library, sklearn. Then we are going to import from scikit-learn linear. This all these various functions. We're going to take the linear model. We're going to import the linear regression. So take note of the capital L and capital R. And from sklearn also we are going to import the metrics for us to do the matrix evaluation, which is the mean squared error. So under the scikit-learn there are a lot of modules. So we are taking from the linear model and we are importing the linear regression function model, and from metrics we are importing the mean squared error. So run this. So I've just shifted to Google Colab. So done with this. Okay, then for us to actually generate and prepare the data for the linear regression, so we are going to randomly generate some random data. So we need to randomly generate of 100 samples, means the x value. So we're going to use the numpy random function and random values. We need 100 values and start with 1. Okay, this is generate 100 samples. So this is x value. We are going to generate x and also y value. Can you all see? Is better. Then we're also going to create the y value. So because we have x, we have generated x random x value 100. So we also going to create random y value, but we will actually create a y value that's offset and also multiplied. So we're just going to introduce offset, but in this case let us actually put a negative offset. So when you put a negative offset, then obviously you're going to get negative linear relationship, and you're going to multiply it with the x value. We are just practically just taking the x values and we are offsetting and multiplying. Sorry, this is the offset. This is offset. This is actually the multiplying. -3, when you multiply, of course you negative, so you get a negative correlation. Then you offset the value. And you use, this is just basically random numbers that you're actually creating, the same thing. So you have x 100 samples of x values, but y values you also created 100. But these are all random values multiplied. So let's run this. I won't give any output because we're just defining the x and y value. So now you want to actually initialize the linear regression model and use it for training by specifying the inputs and output variables as follows. So now we want to initialize the linear model initialization. So we can actually use the regression model. So this is the library that we actually use, imported the linear regression. So this is the function that we actually going to use. So we are initializing the linear regression to regress model, whatever name. Now we are going to try to fit the data, train the model. So we need to use the regress model, and we want to fit, use the function fit. And we are going to fit the x and also the y. So for the regression model that you have initialized, if you have initialized using the linear regression library, you are going to fit the x and y values, which trains the model. So of course you get the output. This is a linear regression output model. And in order for us to actually try to predict the outcome of x and also the evaluate, then we will actually type this for prediction. So let's say we want to actually have the y as our prediction, right? Oh no, not prediction, y predicted. So the model that we have initialized, the name that we use is actually the regress model, and we want to get the predict. So these are the predict, the keywords predict and fit, they are all predefined for the linear regression, and we are going to input the x value. Then we're going to pass the x value to get the prediction. So this is what we're doing to predict the output values from the input x. So we are giving an input x so that it will be able to predict the y using this regression model. And how do we actually do the evaluation? So let us actually find the root mean square. Earlier we will look at the mean square error, right? When you use the root mean square, it actually finds the variance. In other notes, I'll actually will give the description for each one of this. So this one, you need to use the NumPy squared function. Why we're using the NumPy squared function? Because earlier we have already imported the mean squared error, right, which is MSE. If you want to find the root mean square error, then you just need to use the NumPy library and use the squared function. So we already get the mean squared error. And what you want to calculate? The mean squared error, you need to actually give two inputs for it to calculate. The function, do you know what are the two? And the equation is now MSE. What it needs to calculate the error?
Y predicted and Y.
Yes, the y predicted and y actual. So this is y actual and y predicted. So it's fine, but of course you don't have the output yet because we have not displayed it. So now we'll try to print those results out. So let's try to print. Some of the things that we can actually print from here is the regress. When we actually when we initialize the linear model, we actually use the name regress model, right? That one you can actually give whatever name that you want to initialize your model. Basically, the regress model is the regression, linear regression. So you can actually also define the slope. So this one, where can you actually get this slope from? This is the regress model, and this is the coefficient. Y equals to mx plus c, right? The m is actually the coefficient. So you're able to get the coefficient, but this one has underscore. Then you can also get the intercept. This is, I'm just copy and pasting, intercept. So intercept, the keyword that they use is also intercept. I'm going to go underscore. How do you know what are the functions that are readily available? You can actually check on the help file for the linear regression. So you can see what are all this, the coefficient, intercept, fit. And also just now we managed to get the RMSE, right? Root mean square. So we can actually put root means mean squared error. So this one, of course, we already calculated this now. So it's RMSE. Everyone got on this part? Now let us try to plot the x and y first before we try to find what is the predicted value. So we can actually use the scatter plot, and we can actually give the input x and y. These are the two original data, x and y. He can set the color. Let's say we can set it as the red. What else we can do in the plot? We can do label also, right? Plot x label. We're going to label the x-axis as x, and also we're going to plot y label as y label as y. Plot y. Oh, sorry, my mistake. Here the plot function is the plot is this is the option. This is actually I put external one bracket. So you see, you are able to get the slope, which is -3, right? Something. That's what actually we define. Not necessarily that slope has to be -3. The intercept value is 5.5. The root mean square error 0.03. And this is your plot function. This is your original XY data distribution. So is it a linear positive or negative linear? Negative linear, right, is because you can see the slope is on the other side, but you can see it has a linear distribution, right? So you can see, of course, you can see the slope and intercept. The slope and intercept is actually the slope and intercept of the model, which we have not plotted yet. So let's try to plot that for the predicted value. So we're going to use the plot. Why are we using plot? Not use scatter. The linear regression have a straight line, right? So this one we are going to plot xy also, but we're going to use the y predicted. And let's set the color as maybe blue color. and we can actually use plot show, so it will show all both in a single chart. Oh, this is supposed to be comma. Yeah, so now we got it. So can you see this? The blue line is actually your model. You can see the slope and also the intercept at 5.5 with the square mean root error as 0.3. Now what would be the ideal value of the mean root mean square? What do you think would be the ideal value? Should it be small or should it be big? It should be small. The smaller your MSE or RMSE, the better your model is. Is that okay? Larger value means if you have a larger variance, right? So if you have smaller value, that means your model is good. They're able to represent the data correctly. So this is the linear regression. So let me see. Let me open this. We'll finish it off with this one. So you can see the linear regression model has this coefficient and also the intercept attributes for the slope and intercept which we have used. The red points, of course, these are all the original data points, and blue line is actually the linear model by applying the regression. Of course, the metrics that we use to assess generally use is MSE and the root mean square, which is the RMSE, and the mean absolute error. So in another notes, I'll actually do that and explain all these things. But we have calculated the root mean square error of a model, which is actually, what is the error? 0.3. Not this one. Huh? At the time of doing this note, the error was this. But now the error is this. Do you know why? Yeah, because the value we use the random generation for X and Y, right? So because those data are there, so you'll actually have change. Now this is important on the advantages and also the limitation. Is very important for you to know. So what are the advantages and applicability? One thing is, of course, linear regression is, out of all the things, is one of the most simplest one to actually implement. But it actually performs well only if the relationship, this is the important point, the actual relationship between the input feature and the output variable are linear. It works well if they are linear. And of course, from this example, we actually applied linear regression. And we also noted that the relationship between the input and output variable is almost linear, right? There you can see it has a linear distribution. So that's why we actually get a small value of MSE. Now this limitation is very important. So one of the main limitation of linear regression is the assumption of linearity between the dependent variable and also the independent variables. That means the assumption that you are assuming that the labels and also your input feature variables, you are assuming that they have a linear relationship. If it's not linear, your linear regression model won't be accurate. And that's the thing. In the real world, if you see, features are highly not linearly related to the output variable. If it's actually non-linear, then we have to use the non-linear regression, logical regression. And also take note, the linear regression performs poorly when there are outliers in the data. So that is why it goes back to the previous data pre-processing of how to handle the outliers. I did mention this, and this is also one question in your finals. How do you actually deal with outliers if the data is small or data is big? So especially for linear regression, outliers should be handled very carefully. And another thing on linear regression, can it be used? Linear regression is actually meant for continuous data type, right? Can you use it for nominal or categorical data types? Why cannot? If it's in categorical, or this thing is known as the non-linear. If it doesn't have a continuous data type, then you cannot use linear relationship. You cannot use linear regression because it's categorical. How you want to actually represent it in a linear function? It's not going to work. So you have to use the non-linear regression. So make sure you know what type of data set that should be fit into the linear regression. If you try to fit in non-linear, of course you will run, you get something, but your MSE or value is going to be terrible. So take note of the limitations. It's very, very important for you to take note. What are the limitations of linear regression, especially if it's used on a non-linear data set? How would it actually work? All right. So with that, I'll stop the recording.